Hi guys, welcome to Learn Electronics Repair. Today we're going to take a further look at capacitors, so we can call this part 2 of capacitors for beginners and everyone. So this video is going to be mostly practical. I'm going to show you some of the ways in which capacitors behave in circuits. But just before we do that, we need to cover a topic that we didn't discuss in part 1, which is capacitor values. Ratings. How do we specify the value of a capacitor? Well, we know if we watch part 1 that a capacitor consists of two metal plates separated by an insulator or a dielectric. And we also know, if we watch part 1, that we had an analogy with this using electrons and carts and car parks. I'm not going to go through it again, you'll just have to watch part 1. But basically, the capacitance, this is the value of the capacitor, how much capacitance it has, is measured in farads. And this is named after a scientist which you've probably heard of, named Faraday, who did a lot of the early work on capacitors. So how many farads basically specifies how much power the capacitor can charge in the electric field. What electric field? Watch part 1. Okay. Now a farad is a very high amount of capacitance, and in practical applications we don't find capacitors really that are rated in farads, or at least not very often. So capacitors are normally rated as a fraction of farads, and the most common ones is a microfarad, or UF, or a Greek μF if you have a Greek keyboard on your computer. This is 1/1,000,000th of a farad, so it's 1/10000000, 1/1,000,000th. Okay, and even a microfarad is a fair bit of capacitance. We get a lot of capacitors rated in nanofarads, that is 1,000th of a microfarad. And quite commonly in circuits we'll find capacitors rated smaller than that, in picofarads, which is 1,000th of a nanofarad. Okay, so that's the measurement of capacitance. What specifies in the design of the capacitor what the value will be? What makes one capacitor a higher capacitance than another? Well, the main properties are the size of the metal plates. Yeah, these are quite often actually rolled up in a roll, so you'll have physical construction, something like a sandwich like this, where you'll have the two metal plates. I hope I can draw this right. And in between, is this enough of a different colour? Not really. Try this. Much better. Yeah, something like that. Imagine a Swiss roll, yeah, them things with jam in them, yeah, and cake either side. So the jam is the dielectric and the cake is the metal plate. I'm not sure how conductive cake is, and I'm not sure how well insulating jam is. Okay, maybe you guys can go and find out, but that is the basic construction of a capacitor. So by rolling these things up using often aluminium foil and some sort of insulator, you can make larger and larger capacitors. So the area of the metal plates is the first factor, and the higher the area, generally speaking, the higher the capacitance. Another factor which might not be quite so obvious is the distance between the plates. So the closer the plates are together, the stronger the force of the electric field from one side to another. So the distance between the plates also increases the capacitance. The narrower the distance, the higher the capacitance for a given area of metal plate. And the third one, which may be even less obvious, is the quality of the dielectric, what we use for the dielectric. So some materials create a higher capacitance than others, again for a given area of metal plate. So those are the three factors. But there's an important thing here, and this is obvious, but I'm going to tell you. The closer together the metal plates are, the lower voltage you can apply across the capacitor before this dielectric breaks down. The thinner the dielectric, the less voltage potential it can withstand either side of it. That does make sense, yeah. I mean, if we use air as a dielectric, which we could do, you can have high voltage on two probes and nothing happens. But as you get closer and closer and closer, and you've seen this in Frankenstein films and such like, no doubt, at a certain point the air will arc over and you now have a breakdown of the dielectric. In fact, once it's arced over, you can move them further apart because it'll continue to arc over. That's something else. But anyway, that is the point. The closer together the metal plates, the lower the voltage you can withstand. Again, that will depend to some extent on the type of dielectric. Fourth factor, how thin can you make the dielectric? I mean, how thin can you make a piece of paper or a film of plastic? There's a limit, yeah? So to get very, very high capacitance in a small device, we need the plates to be extremely close together. And the way that's done is with electrolytic capacitors. So with the electrolytic capacitor, you have your two metal plates suspended or rolled up in a liquid, a chemical, yeah? And what the chemical basically does, and I'm not a chemist, but what it basically does is it causes one of the metal plates to become oxidized. A bit like, imagine you put a piece of iron outside or steel, yeah, after a while you get rust on one side of it, don't you, or both sides. Well, this is a similar thing. Now, you know yourself that rust or tarnish on silver or anything like that can be very, very thin, much thinner than you can actually make a physical plastic sheet or something similar. So by using this process, electrolysis, to make electrolytic capacitors, you can get an extremely thin dielectric. The only disadvantage, if you can call it a disadvantage, to this is that the chemical process is a one-way thing. So these capacitors are polarized. They work in one direction only. And when I say one direction, I mean in one polarity, positive to negative only. So on a capacitor, we're going to find three ratings, if they're marked, all of them. We're going to find the capacitance, which is in one of these. We're going to find the voltage. This is the maximum working voltage. It doesn't mean the capacitor works at that voltage. It just means the capacitor will not work above that voltage. What happens if you exceed that? Well, we're going to find out shortly, okay? And the other one on these type of capacitors is the polarity. They're marked plus and minus on either end. We now know enough about capacitors to start to do some practical experiments. So let's play around with capacitors for a little while and let's see what we think. And above all, let's have some fun, yeah? So here is a breadboard. This allows us to experiment with components easily without messing around with soldering irons and such things like that. Mine's got a nice hole in it, by the way. Somebody asked about this on the previous video. How did this happen? Well, we have a live stream on a channel called The Electronics Channel. And if you want to know how that happened, go watch the live streams, yeah? But hopefully we're not going to do the same thing today. Of course, we need a few components as well to conduct these experiments. So we're going to have some resistors. We talked about resistors earlier, so you'll know about these. This is a 22 ohm resistor. This is a 220 ohm resistor. These are not brown, they're red. My camera picks the colour up wrong. This one is a 22 kilo ohm resistor, or 22,000 ohms. So we have an increasing value, a few resistors there we can play with. Here is a capacitor. This one is, we can see 473J. 2A actually specifies the voltage. You can look that up. 473 is the value in capacitance. It's 47 nanofarads. The J, if you wondered, that is actually the tolerance, 5%. This one is a larger capacitor. It's physically larger, as you can see. So 2A again specifies the voltage, 474 is the value. That is 47 and 4 zeros, or 470,000 nanofarads. Again, J is the tolerance. And we have one more. So this is an electrolytic capacitor. 2,200 microfarads, 16 volts. So this specifies the voltage and the capacitance. This is also polarized, so this is the negative end. By default, the other end is the positive end. The brand, or ESR, we'll talk about ESR later, but not in this video. We don't need that right now. And the temperature range on this as well, the working temperature range, because this is a electrolytic capacitor, it has a liquid inside it. Therefore, as all liquids do, they boil and they freeze, hence we have a temperature working range. Also, to complete our circuits, we need some sort of indicator. This is an LED, light emitting diode. We haven't talked about these yet. You may well have heard of them. Imagine this like a light bulb, basically, but it also needs a resistor in series with it to limit the current that flows through it. Otherwise, the bulb will blow. So don't worry about it too much. It's just an indicator so we can see what's happening in our circuit. We'll cover these in detail a little bit later, of course. So now for our first circuit then, we're going to take a power supply. We're going to use 12 volts. Here is your first ever circuit diagram or schematic. If you really are beginning, this is your positive supply. This is your negative or 0 volts. This is the capacitor. Okay. And then we're going to connect here our LED, our indicator light, with the resistor to stop the current flowing too high. Another symbol for you, this is an LED. The arrows represent light being emitted, LED, light emitting diode. And that's the circuit, okay? I'm going to put a 390 ohm resistor in here. That's just to prevent too much current flowing through the LED. Otherwise, the LED won't like it. In fact, I will show you that straight away. And here is our circuit on the breadboard. But what I've omitted at the moment is this resistor. So the LED isn't actually connected at all. It's there, just you can see one end of it goes nowhere. Okay. These breadboards, by the way, if you're not familiar with them, just briefly, each strip of holes, 6 holes, is connected together. In fact, you can see, because this one's burnt, there's a set of metal clips which runs across here under each set of holes. So effectively this, which is the negative supply, 0 volts, ground, however you want to call it, we'll talk about that later as well. This is the LED, one end of it, and this wire actually goes to my multimeter. You can see that's connecting to the negative probe on the multimeter. You can see the multimeter here. And this row of pins where this red stripe is, they're all connected together. So this is a 12 volt supply. You can see the multimeter positive lead is connected, and you can see we have 12.037 volts. So that is basically 12 volts. Now I mentioned that these LEDs require a resistor to limit the current. And I don't want you to take my word for that. I want to prove that. So I'll just turn the voltage supply off. You see the multimeter's gone to 0. I will now connect the 12 volts to my LED. Okay, so the LED is now connected. We'll get a good look at this, and I'm going to switch on. This is a red LED, so it should light up red. Okay, let's try it. Well, it flashed once and it went off. If I switch the power off and back on, it won't flash again. And that's because the LED is now dead. So, first of all, we need another LED. And this time, we need to make sure that it doesn't commit harry-carry like that. So, there is our LED, and we're going to connect a resistor in series with this. So, from this end of the LED, we need to connect a resistor. Okay, and now we can connect our power to the LED via the resistor. Yeah, now let's switch the power on. And now the LED lights up red, just as we would expect. We can see 12 volts on the meter. If I switch the power off, the LED goes out. Switch it on, the LED goes on. If you watch part 1, you will know that capacitors store electricity in an electric field. So what happens if we add a capacitor to our circuit? Well, here's the 47 nanofarad capacitor. Okay, you can see there, 473. So we'll connect our capacitor exactly how we showed it in this circuit. So between the 12 volts and the ground, or 0 volts, from positive to negative. So what should happen now is this capacitor should charge up to 12 volts, and when we switch the power off, the LED should be able to run from the capacitor for a little while. So let's see what actually happens. Well, the LED lights up, and the LED goes back out, just like it did before. Okay, on, off, on, off. Okay, so the capacitor in fact doesn't really seem to do anything. Why is that? Well, the reason for that is the capacitor is too low a value to keep this LED lit up for anything other than maybe microseconds. So we'll fit a larger capacitor. So this is the 417 nanofarads. This is 10 times the capacitance of the other one. What happens now? Power on, LED lit, off, LED out. So still, we don't see any difference. Let's try much higher. So this is 2,200 microfarads. This is a bit over 4,000 times the size of that other one in capacitance. This is rated at 16 volts, and this has a negative, and it's marked negative positive. Okay, so let's add this capacitor to the circuit, and we'll conduct the same experiment. So we'll put the power on, the LED lights, we'll take the power off. And look at the voltmeter. So what's happening is the capacitor is now discharging into the LED, and gradually the voltage gets too low for the LED to be lit. It goes out. Okay. There. Power back on. Power off. So you can see that a capacitor does in fact store electricity. It's just to get any appreciable difference with an LED, we need quite a large size capacitor. What sets the amount of time that the capacitor takes to discharge? Well, it's the current that flows through the LED. the higher the current, the faster it will discharge the capacitor. And we can actually show that. This is a 100 ohm resistor, so it's about a quarter of the value of this one, okay? Let's put this in our circuit. Okay, there's our 100 ohm resistor. Let's apply the power again. So the LED is lit. Now let's take the power off. Well, I hope you noticed that the LED went dimmer faster, okay? It discharged faster. So we can see that the rate at which the capacitor discharges depends on the amount of current being drawn from it, okay? Take this out. Notice, by the way, it now actually climbs up slightly. That's a strange property of capacitors called recovery. When you stop drawing current, it won't charge all the way up. It'll just charge back up a little bit, but hey, you may as well see it now, because otherwise it will just confuse you when you do see it later. That recovery effect actually with an electrolytic capacitor is in part due to the fact that there is a chemical reaction going on inside here, okay? Or rather, there are chemicals inside there. Let's connect a higher value resistor. So this is a 1000 ohm. You can see, actual fact, now the capacitor is discharging again. So the power's off. There was just enough power left in the capacitor to light the LED again. Once the LED lights, it starts to draw current and the capacitor starts to discharge. Another thing you'll probably notice is that the capacitor does not fully discharge. That's because the LED, once it gets down to a certain voltage, around 1.5 volts, stops conducting actually and stops drawing any power. In the meantime, while we've explained a few of the stranger properties that other people don't ever tell you about, I've put a 1000 ohm resistor in. So this is a bit more than twice the size of the first one we had. So we should know that the capacitor will charge up. And when I take the power off, it will now discharge slower because I'm drawing less current from it. Okay? Taking quite some time. What happens if we fit a very high value resistor? Well, this one is a 220,000 ohm resistor. This is a very high value resistor. Let's fit this in our circuit. Okay. Multimeter wants to go asleep. Let's put it back on again because we're all very much awake, aren't you? Yeah. Let's try this. So we now have a high value. And we put the power on and we got 12 volts. But I think the first thing you'll notice is that the LED isn't lit. Why isn't the LED lit up? Well, this resistor is such a high value that it can't supply enough current to the LED for it to light. The LED can't light because it doesn't have enough current flowing through it. The higher the value of the resistance, the lower the current. Remember the early lessons we did, Ohm's law? Well, there's some more proof this is true, yeah? So, let's see what happens now if we take the power off. And the capacitor is discharging, it's just taking time. And the reason it's taking time is there is some current flowing through here, but very, very little. So what happens if we take the resistor out altogether and we charge our capacitor? There's no current flowing now. There's nothing to discharge our capacitor. Do you think it will just continue to hold the voltage that's in it? Well, let's see. No, you see, it's still discharging. Why is it discharging? Well, I'll show you. With a capacitor, and this is an electrolytic capacitor, which is polarized, by the way, and it has a different symbol. There are a few variants on this, but we'll just use this one. This is the positive end where the wide bar is, okay? Now in between is an insulator, the dielectric, but an insulator is never a perfect insulator, especially with electrolytic capacitors, because this is just a metal oxide film in an electrolytic solution. It has a certain amount of leakage resistance. So effectively there is a resistor inside the capacitor like that. And that's not because somebody put a resistor in the capacitor. This is a byproduct of the manufacturing technique used for these types of capacitors. So it will discharge, but it will take a very long time. And when I say very long time, this depends on the voltage that's in the capacitor. This is why you've probably heard this and seen these warnings on high voltage mains powered electrical equipment, that the equipment, if you open it, may contain high voltages when it's not connected to the mains. And this is why, because capacitors and that sort of equipment can charge up to 300, 400 volts. Yes, I know your mains is 110 or 220, but there is often a booster circuit in there to increase the voltage. We'll talk about that much further down the line, but for now, know it's there. So it's quite possible to have 300, 400 volts stored in the capacitors and a piece of mains powered equipment for a very long time afterwards. You can see now this one's dropped by about a quarter, and we've been talking about it for a while. So do not touch the terminals of a capacitor, especially a high voltage one, without checking first with a multimeter to see if it stores any voltage. So we've learned that the capacitor does store electricity, but to get any appreciable, notable to us amount of electricity, we need quite a high value capacitor. And we've also proved that the rate at which the capacitor discharges depends on the current that's being drawn from it. And the same also applies to the rate at which the capacitor charges. So if I just modify our circuit slightly, what I'm going to do now is to connect the plus 12 volts again via a resistor to our capacitor. 0 volts. This is your plus and your minus, okay? And I'm going to connect a resistor here. So this is a 220 ohm resistor, one we were playing with before. There's our circuit. We don't have an LED on here anymore. We can connect our multimeter again, but now we're going to measure the voltage, not the 12 volts coming in. We're going to measure the voltage on our capacitor. Okay, so we're connecting our multimeter to measure the voltage from here to here. Okay, let's see what happens. Well, straight away, without connecting any power, we can see there's still some charge in our capacitor. So to get rid of that charge, I'm just going to short the capacitor out. And I've now discharged it. See the little bit of recovery I was telling you about? Wait a little bit longer. Once again. And you'll see our capacitor is pretty close to discharge now. It's got about 0.02 of a volt in it, 0.03, not very much. Okay, so let's now connect the power and see what happens to the voltage in our capacitor. And while I'm talking, by the way, you'll see that that is now discharged again. This is this kind of like bounce back thing. Maybe we can talk about that in detail at some point. To me, it's just something that capacitors do, and I don't overly worry about it, okay? But if you want to talk about it, comments below, guys. In the meantime, I've connected my power supply, so let's now see what happens to the voltage across the capacitor when we charge it via our resistor, 220 ohms. Okay. Well, you can see it charges up, but it doesn't do it straight away. And the rate at which it's charging, if you look, gradually slows down. Okay. Switch the power off. It will start to discharge again. What if I put a higher value resistor in here? Well, we'll go a long way. So again, this is my 220,000 ohm resistor. Okay. I put a very high value resistor in there. Let's switch the power back on. It's down to about 0.7. It's fairly low. In fact, if we really want to, let's just short out the capacitor again to get a comparative reading. Okay. Let's put the power on and watch what happens. So we can see the capacitor's charging up, but it's charging up very slowly. That's because the resistor I'm charging it through is now a very high value resistor. It will charge up, but this will take time. In fact, so much time, this video would go on forever. So I'm going to use a 22,000 ohm. Yeah, something 10 times smaller. Let's have a look. Okay. Now you can see it's still charging fairly slowly, but quite a bit faster. So the rate at which a capacitor charges and discharges depends on two factors. One is the value of the resistor that it's charging through, and the other is the value of the capacitor that you are charging. The higher the value of the capacitor, the longer it will take. The higher the value of the resistor, the longer it will take. And there's a name for this, and it's called the RC constant. There's also a formula that lets you work out what the time will be. Another thing you'll notice now, because I've left it a little while, is not only does the time it takes to charge or discharge depend on the value of the capacitor and the resistor, but can you also see that the charging rate has slowed down? The nearer it gets to the full supply voltage of 12 volts, the slower and slower it charges. So that's another important thing to notice about capacitors. Now we could go into RC constants and we could start to do some mathematics, but I think you guys will be happy enough to see that in principle at the moment. Maybe we can talk about the maths later, but for now let's look at a few more interesting things. So the first interesting thing then, if we know the rate of charge and discharge of a capacitor depends on A, the capacitance, and B, the resistor, which is limiting the current it's charging. In other words, the charging current. How fast can we charge a capacitor if we don't put a resistor in there, if we just connect it to a power source? And particularly, how fast can we charge something like this bad boy? So this is a 10,000 microfarad, 100 volt rated capacitor. Okay, how fast do you think we can charge this? Well, let's find out. There's my multimeter. You see this capacitor's got 10 volts in already. That's been sitting in my cupboard for quite a long time. We need to get rid of that. Let's use our 22 ohm resistor, a low value resistor. That should prove to you that capacitors can hold a voltage for a long time, because this was last used a couple of weeks ago on the live stream. Okay. I think we've pretty much got rid of that. You'll see the bounce back, of course. Okay, that's fairly well discharged. How fast do you think we can charge this thing up? I've set my power supply to 32 volts because I can, and because the capacitor can handle that. Yeah, I'm not quite sure if I can handle this, but for you guys, let's see. Well, the answer was instantly. I thought we might see some sparks there actually, but we didn't see any spark. But we do have a very strong voltage charge in our capacitor. How fast do you think we can discharge it? Yeah, if we short it out with this black lead. What do you think it'll do? How long will it take? Okay, well, the answer was not very long. Okay, so a capacitor, you can pretty much charge it and discharge it instantly. In fact, so fast that normally you would have parts of the circuit connected in such a way to prevent that from happening. It's not very good for the capacitor to charge and discharge that fast, because as you do it, you put an extremely high strain on the dielectric inside the capacitor, and B, it's not particularly useful. But there are some sort of circuits, trigger type circuits for high voltage flashlights. I don't mean flashlights like a torch, I mean like the stroboscopic lights, where you want to discharge a capacitor extremely rapidly into a xenon tube to get a very short duration flash, photographic flash, that sort of thing. So there are circuits where you will want to do that sort of thing, but you will generally have special capacitors in those circuits to make sure that they can do it. So that's how fast we can discharge a capacitor immediately, pretty much. Here's an electrolytic capacitor, 2200 microfarads, 6.3 volts. I did mention earlier that this is the maximum working voltage for a capacitor. So what happens if you put more volts than that in? I think you probably want to find this out as well, so let's try it. Well, here we have our capacitor. I'm just going to clip it onto this stand to keep it in place rather than just lying on the desk. I've connected the power supply. We can see the capacitors there. I've actually set the power supply to 32 volts, so I know exactly what's going to happen. You guys may know what's going to happen, but you're going to find out at the moment, and I think I'll just leave you all to it. Yeah. It didn't explode. Hope you enjoyed that. It didn't explode. Sometimes these will just explode. Yeah, this one, you can see what it did. It was all right for a few moments, and then out came the magic smoke. So what happens in this instance is one of two things. Either the magic smoke comes out like so, or the magic smoke comes out so fast then the thing explodes. Okay, so that's what happens if you put too much voltage on a capacitor. Okay, I think there's enough for one video there. Hope you enjoyed that. There are quite a lot more experiments I want to do with capacitors, so in the next part we will continue with our practical investigations. Get into the comments below and let me know, guys, and I look forward to seeing you all soon again on another Learning Electronics Repair video. Ciao for now, guys.